Chapter 3 is all about the periodic trends occurring on the periodic table of elements. What we see on the periodic table is that there are some recurring patterns that occur, both in physical and chemical properties of elements, and it's actually been helpful to help scientists predict elements that hadn't been discovered yet and understand how they behave. So for example, we have boron, and right underneath it on the periodic table is aluminum, then gallium and indium. So they're in the same family or group. And as you go down the periodic table, you tend to see that the density increases. As a reminder, density is mass over volume. And so one of the trends is that as you move down in a column, that the density increases. We also see trends such as atomic radii and ionization energy and lots of things like that occurring, both happening as a family and as a period. So recurring patterns like that, the repeating patterns, that's why it's called the periodic table, because there is a repeating pattern that occurs on it. In the 1800s, scientists were noticing that certain elements had similar properties. So Mendeleev in the mid-1800s summarized that as the periodic law, which says that when you arrange elements in order of increasing mass, then the properties are going to recur periodically. So we're going to keep cycling through and see similar things. So initially that was the format, and then he arranged the rows so that the elements that had the similar properties fell in the same column. Right, so that is the group. And in some of these columns, we're arranging it in terms of mass and grouping within the column, there were some gaps. So that helped to give them a hint that there might be an element that should go in that spot. And it actually did help them predict some undiscovered elements at that point. So for example, what they had as silicon, which is very similar to silicon, ends up being germanium. They predicted, based off of where it should have gone, that it should have a mass of 72. It basically does. That its density should be about 5.5. It's pretty close. That it would act with an oxygen and chlorine with that formula, and it did. We also see similar predictions with gallium, which was similar to aluminum. So now we have elements that are actually, instead of listed in order of increasing mass, they're actually in order of atomic number, so number of protons. And then where our rows are those periods, so going across is called a period, and going down, up and down the columns are the groups or the families. So they have similar properties, just like you might have in your family. So the periodic law, right, it's a law, helps us to predict the patterns, but it doesn't explain the why. And what we just learned last class, that quantum theory helps us to explain the why behind this, these trends that we see. So we have different groupings on the periodic table, and it's actually very sophisticated for how common it is. But we classify elements as metals, nonmetals, and metalloids, which have properties of both. We could also divide the periodic table into main group elements. These are ones that are listed with an A at the top, and then we have transition elements and metals. And these are the ones that are listed with a B. They're less predictable than the main group elements. Those tend to be quite predictable, but the transition metals have a little bit more variability to them. So here we can see these letterings with 1A, 2A, 3A, 4A, and so on. These are our main group elements. Main groups are here and here. And then our transition elements are here, the blue ones, and then also down here. We also have I'll do it in pink, metals are on the left of this little stair step, the zigzag here. So metals are over here, and then we have nonmetals mostly here, and then our metalloids are on this kind of touching the line. We can use quantum mechanics to help us understand how the electrons are behaving in an atom. We know that electrons exist in the orbitals. And remember, we have s orbitals, p orbitals, d orbitals, and f orbitals. And how we describe that is it's called the electron configuration. It's kind of like the address. So for hydrogen, we know that hydrogen has one electron because it has one proton. So the lowest energy level it can have for an orbital would be the 1s orbital. And since there's one electron, we'll put a 1 there. So this number out front indicates the energy level. The letter F represents the orbital type. So remember, energy is like the n level. Orbital type is the L quantum number. And the number up here is the number of electrons in that subshell. So how we would draw that as a orbital diagram is we would draw a line indicating that one orbital that exists. If you remember, when L equals 0 for s orbital, m sub L equals 0. There's one number, meaning one orbital. So we'll label it as 1s. And since there's one electron, we're going to put it as spin up. Now, as we get to more electrons, so anything other than hydrogen, we are going to approximate the equation because it can't actually be solved when there's more than one electron. But hydrogen tends to be pretty good approximation. So the approximate solutions show that hydrogen is good enough. But key thing here is now we have multiple electrons, so the m sub s, or the electron spin, matters. And then we're going to also have some repulsions happening. So we're going to increase energy a bit as we have more electrons. So not all the orbitals won't all be at the same energy level, even within the same shell. We're going to have some splitting of energy levels. So like we talked about last chapter, the m sub s, or the spin quantum number, is a fundamental property of the electron. They're all the same value. It's all a half. Their orientation is just different. So when we have a spin up, we call the m sub s is plus 1/2, or when we're spin down, our spin quantum number is negative 1/2. And we could use orbital diagrams to help visually represent the electrons. We do it with a half arrow indicating the spin. So when we draw the arrow up, we mean spin 1/2 up. It would look like this. When we are talking about spin down, we do it down like that. Notice I'm just doing kind of like a half arrow, not a full arrow. When we have more than one electron in an orbital, they need to cancel each other out. And so we're going to have one spin up. So they need to be paired. That's what I mean by cancel out. So we'll have two electrons with opposite spin, one spin up and one spin down. So the Pauli exclusion principle tells us that no two electrons in an atom can have the same set of 4 quantum numbers. Every electron must have its own unique set, right? So keeping in mind the set being N, L, M sub L, and M sub S. So, for example, if I have helium has 2 electrons, so it's going to be in the lowest energy level is 1. Then that energy type, or the orbital type, is S. And we have one s orbital, and we can fit 2 electrons in there. So if I was to draw the orbital diagram for this, I would label it as 1s, and I would do 1 spin up for the first electron and 1 spin down for the second. So we have 2 electrons in there. So we're going to have, let's do the quantum numbers. First, let's talk about the quantum number for this first electron. So its n value is 1. Its L value for an s orbital, L value is 0. The only m sub L is 0. And then it's spin up, so it's positive 1/2. So that's its set of quantum numbers. For this other electron, right here, we're going to have, it's also in the first energy level, also in an s orbital which only has 1, and it's -1/2. So its set is different than that set. So they are distinguishable. So this configuration satisfies the Pauli exclusion principle. A bit of terminology. So when an orbital has the same energy level as another, they are said to be degenerate. So before, when we had hydrogen, I'm just going to pull to the side. From our last set of notes, we had the 1s orbital here. And we saw before that when we're at the 2 energy level and then third energy level, right, n equals 2, n equals 3, we increased in energy. What we also had, though, is we had the p orbitals. So I had 2s, I had 2p. I have 3s, 3p, and 3d orbitals. And these, so every orbital on the n level, n equals 3, was degenerate. Every orbital on the n equals 2 level was degenerate, meaning they're at the same level. Now, once we have some, and this is only the case for single electron situations, so like hydrogen. There's only one electron, it can kind of bounce wherever it goes. It doesn't have to deal with any kind of interactions with other electrons. But once we get to any other type of atom that has multiple electrons, the sublevels start to split. And this is because of, really a lot of it is charge interactions, right? These electrons getting close, we have more electrons, they're fitting in the same orbital, they're going to repel each other. And that repulsion causes the electrons to increase energy. If you remember, we talked about in class, low energy is stable. So when we have it, this is mostly like attractive forces are going to be low. Once we have repulsions, we're going to have higher energy. And that shows up here. So here we can see, here's my 1s, cool. 2s is up, and now 2p, instead of being on the same level, will split up. Now all the p orbitals are degenerate with each other, but they're not degenerate with 2s. Then we have 3s, 3p, 4s, and now, interestingly enough, the splitting between 3p and 3d is so big that 4s is actually in between. And luckily for us, our periodic table is built in such a way that we don't have to worry about memorizing this order. We can use the periodic table to help guide us. So the lower the value of the L quantum number, the less energy. So s orbitals are lower in energy than p, which are lower than d, which are lower than f. So the Aufbau principle tells us that as we fill orbitals with electrons, we start from the lowest energy and move up. So if I have something like lithium, which has 3 electrons, I'm going to first fill up 1s and with 2 electrons, so 2 are gone, and then I'll come up and fill my 2s. And then as that fills up, I'd go to 2p, and then 3s, and then 3p, and then 4s, and then 3d, in that order. So from low energy to high energy. Don't worry about memorizing it. I'm going to teach you a strategy. So once again, we're going to talk about Coulomb's law because even though it's a physics equation, it explains a lot of the interactions and the energies of these charged particles that we're dealing with. So Coulomb's law says that the energy between 2 charged particles equals a constant, we'll call it K, multiplied by the charge of particle 1 times the charge of particle 2 divided by the radius, or the distance between the two. When we have like charges, like 2 positive or 2 negative, we know that they repel. And so we have a positive times a positive over a radius is going to be a positive number, or negative times negative will also equal a positive number. So positive energy is for repulsive forces. When we have opposite charges, we have a negative times a positive divided by that radius, right? Then we have a negative potential energy. So when we have negative energy, that is similar for when we have attractive forces. So negative values for energy is for attractive forces and positive is for repulsive forces. So when we have electrons, multiple electrons together, we're going to have some attraction to the nucleus, but some repulsion from each other. So basically, if we think about, here's our nucleus, it has our positive charge, and then we have our electrons in the various shells. As the electrons are closer to the nucleus, they're going to feel that force really strongly. Then we have electrons in the outer shells. They're not as close to the nucleus, so their energy is higher. So we are closer to a positive number compared to the ones closer. And they're also going to be kind of blocked. So this is called shielding. It's when electrons are on the outer edge are shielded from the total charge. So it leaves them having a net charge. So how we can calculate that is we say, how many protons are in the nucleus, so that's our proton number or atomic number, minus how many electrons are shielding out here in the core. So we put minus the shielding. And this is going to be the net charge that the outer electrons fill. This is called effective nuclear charge, or Z effective. So the total attraction that the outer electron fills toward the protons in the nucleus. So if I have something like lithium, lithium has 3 protons in the nucleus. And if we look at lithium, it has it's 1s2 and it's 2s2. Nope, 2s1. So it's going to have 1 electron in the 2s shell. So in that first energy level, these 2 electrons are actually shielding the outer electron from the nucleus. So we have, right, a +3 in the middle. We have these 2 electrons here and 1 out here. So this outer electron, it's basically getting canceled out by these 2 electrons in the inner shell. And so the effective nuclear charge of the outside electron is going to be 3 for that total protons in the middle, minus the 2 inner electrons. So it's only going to feel a +1 charge. So a couple concepts. We talked about shielding already. Again, it's how much an outer electron fills from the nucleus if the inner electrons are shielding it. So here we see, here is lithium again, right? +3, 2 inner electrons shielding, so this outer electron fills a +1. And the closer an electron is to the nucleus, the more attraction it feels from the protons. And that makes sense. So these inner electrons here, they're feeling the full +3 charge, and so they're pulled closer to the nucleus. And then our outer electron, it's not feeling as much of it, so it's further away. There's also some variation between the types of orbitals. So S orbitals are actually better shielders than P, D, and F, and that's just because there's more nodes in P orbitals, D orbitals, and F orbitals, so there's more possibility for penetration to happen where the electrons can get closer to the nucleus just because of those nodes. And S orbitals, we know they're a full sphere, there are no nodes, and so they're better at shielding the outer electrons from the nucleus. Now we're going to talk about electron configurations. We did talk about it for hydrogen already. We know that hydrogen has 1 electron, so it's in the lowest energy level is 1, there's only an S orbital, and there's 1. So that's an example of an electron configuration. When we have multi-electron atoms, so anything above hydrogen, we're going to want to fill from the lowest energy to the highest energy. So we're going to start in our S orbitals, P, D, and F. So for example, for lithium, lithium is the 3rd element, and so it's going to have, it's going to fill the 1 S orbitals, and we know that there's only, of S orbitals, there's only 1, due to the M sub L level only having 1 value. And then it's going to fill it up with 2 electrons. So 2 electrons fill every orbital. And then we have our second level, 2s. So S is the lowest energy compared to P, so it'll show up first. And we only have one electron left, so we'll write 2s1. So how I would write that orbital diagram is I would label boxes. Here's my 1s, here's my 2s, and I'm going to draw arrow up, arrow down for my 1s2, and then 2s just has one electron. So that's how I would draw for lithium. Now, for orbitals that are the same sublevel, so if it was a p orbital or a d orbital, they are degenerate with each other. So px is equal to py, which is equal to pz. So remembering Pauli exclusion principle, it said that we can't have 2 electrons in an atom. Sorry, exclusion. We can't have 2 electrons within an atom that has the same quantum number. So this is basically saying I can't have 2 spin ups. That cannot exist. So I'll have a spin up and a spin down. Because if I had this situation, I would have both of those electrons would have the same set of quantum numbers, and that violates this principle. We also have Hund's rule, which says that when I fill orbitals that are degenerate, you want to fill all half full and then come back and pair them up. So for example, carbon. Carbon is element 6, so it fills up the 1s2, then it does 2s2. Now it has p orbitals, so we have 2p, and since there's 6 electrons, we're only going to have 2 in there. So when I draw, so that's the electron configuration. When I draw the orbital diagram, I'll label it 1s, I'll label it 2s, and then we know that we have 3, when we have p orbitals, there are 3 of them, so we'll label that 2p, and we draw 3 boxes for the 3 orbitals. So fill up 1s2, 2s2. Now it's 2p2, so what we don't want to do is fill it like that. That violates Hund's rule. Hund's rule says that it's energetically more favorable to actually spread those electrons out, put them in different orbitals because of electron repulsions. They don't want to be together if they don't have to. So we're going to put them in those separate orbitals, and since their energies are degenerate on that 2p, then they will fill up all of them first, halfway, and then we would come back and pair up. So let's do oxygen. Oxygen has 8 electrons. It's 1s2, 2s2, 2p4. So 2, 4, 8. So we are going to have a similar thing here. We have 1s, 2s, 2p, and we're going to fill up our 1s, 1, 2, fill up our 2s, 1, 2, and then we're going to do our p. So for Hund's rule, we're going to fill up all the way half filled, 1, 2, 3, and now that we have one more, we'll come up and pair the last one. So by pairing each of those orbitals, you're allowing the electrons to spread out, and then only when necessary, you'll go back up and pair. So just to kind of get an idea how to use the periodic table for this, because you might be wondering, how does she know what order to do? How does she know what to do here? We actually get to use the periodic table because it is a beautiful, beautiful thing. Periodic table is basically broken up into those 4 quantum sublevels, S, P, D, and F. So in our group 1 and 2 here, this is our S block. You can pretend helium's right here because you see how it's over here. It's blue because it fits over there. It's our S block element. And then we have our P block elements. They are, oops, we'll do pink here, right here. Our D block is going to be, oops, right here. And our F block elements are going to be right here. So we're going to use the group number tells us, so the group number tells us how many valence electrons for that element, specifically of main groups. So if it's in group 1, it has 1 valence electron. If it's in group 2, it has 2. If it's in group 3A, it has 3. 4A, 4, 5, 6, 7, 8. That's how many outer electrons there are. The row number tells us the highest principal quantum number, so that basically the energy level. So just to kind of give you an idea, let me do it with black. Okay, so if I was, let's say I was trying to find the electron configuration of phosphorus, and I wanted to do the full one. You're going to start at the top of the periodic table. You're going to read right to left, or left to right, just like you would read a book. So you're going to start here. You're going to say, I'm on the first energy level in the S block. I have to go through that. So I have 1s2. Then I come down a row. I'm on the second. 2s2. Keep reading left to right. 2p, now I'm in the p block, but I'm on the second energy level, so 2p, 1, 2, 3, 4, 5, 6. Well, I'm not at phosphorus yet, so I have a 1s2, 2s2, 2p6. So now I'm going to go down to the third level. 3, I'm in the s block, s2, I moved over to 3s2, and I'm going to go all the way over, and I'm going to hit up 3p, 1, 2, 3. So 3p3. That's a full electron configuration to get to phosphorus. If I wanted to get somewhere like iron, keep in mind what we're going to have happen. We're going to go all the way through 3p6, come down to 4s. We'd have 4s2. And then the D block actually starts here at 3d. And if you remember the energy level splittings, the d electrons actually, or the d orbitals, are higher in energy than the 4s due to some splitting. So the d orbitals start here, so we'd have the 4s2 we pass, and then we go 3d, 1, 2, 3, 4, 5, 6. So 3d6. That's how you use a periodic table to help you figure out electron configurations. Key things you need to remember is that D starts at 3D, and then you'll pop back up at 4P over here. So D is always going to be one energy level below where your S and P are, and then F block starts at 4, and it doesn't start until down there by lanthanide here. All right, so quick summary. When we do electrons in orbitals, they're going to occupy to minimize energy, starting with the lower energy orbitals first before you fill the high ones. Here's the ordering, but we're going to use a periodic table. Every orbital can hold 2 electrons, and when they are in the same orbital, they're going to have opposite spins, so they don't have the same set of quantum numbers. And ideally, if we have degenerate energy levels or degenerate orbitals, they first singly fill in and then pair up. That's Hund's rule. And just to help you remember, this rule here is the Aufbau principle, saying fill from low energy to high energy. So you do need to remember Pauli exclusion principle. I'll highlight them. You need to remember Pauli exclusion principle, Aufbau principle, Hund's rule. Where'd you go? Hund's rule. Yeah. So make sure you have a periodic table out for this. You're going to write the electron configurations for each element. Knowing the periodic table is going to be really helpful, so you can do that. All right, magnesium. Magnesium is element level, or element 12. It's in an S group. So we're going to start with the 1s level, 1s2, 2s2. We have to go all the way across to neon, 2p6, and then go down 3s2. So we count up those electrons in the superscript. We have 2, 4, 10, 12. Now we actually did phosphorus on the other slide, but we'll do it again. It's on the third level down, so it's going to be in a 3p block. So for phosphorus, it is number 15. And we're gonna do the same ones as magnesium. We're gonna go 1s2, 2s2, 2p6, then 3s2, and now we have to go over to the 3p, and then we have 3 electrons in, 3. So 2, 4, 10, 11, 12, 13, 14, 15. Okay, I'm gonna pause and let you try bromine, chlorine, and osmium on your own, and then you can peek in and see the solutions. All right, so if we look at the different elements, we first have bromine, it's element 35. We're gonna go through the 1s, both two energy levels, 2s2, 2p6. We then have 3s2, 3p6. Now we're down at 4s, and we have our 3d showing up. We go all the way through the 3d, and we end up at 4p5. Notice 4s and 4p are on the same energy level, and d is a little bit below as far as the energy number. For chlorine, it's right above bromine, so it's going to have the same number of p electrons are in the same group, but we're not going to have this whole level, basically. So we have 1s2, 2s2, 2p6, 3s2, and then 3p5. And then, this should be osmium. It is really far down. It's number 76. You probably had a hard time finding it. I did, actually. So we're on that, if we find it, we're on the 6th energy level. So we're going to go all the way down to n equals 6. So 1s2, 2s2, 2p6, 3s2, 3p6. Now in the 4th one, so this is where the D's start to come in, 4s2, 3d10, 4p6, cool. 5th energy level, 5s2, 4d10, 5p6. Now we have, if you look at your periodic table, you see a little insertion where the p orbital or the f orbital is in there between the s and the d. So we actually have 6s2, then we have 4f14, and then our 5d orbital shows up and we go in 6. So with this problem, we're going to do electron configuration for sulfur, then do the orbital diagram, and then count out how many unpaired electrons it has. All right, so sulfur is element 16. Whoops, I'll do it down below. Okay, so that means we're gonna go, it's on the 3rd level. So we have 1s2, 2s2, 2p6, fill up that 2nd level, 3s2, and then 3p4. So for my s orbital, I'll have one of them, 1s, 2s. My 2p is going to have 3 levels, 2p. We have one 3s orbital and then 3p's. All right, so we're filling up 1, 2, filling up 1, 2, go all up, and then all down, Hund's rule. 2p is filled. Now 3s is filling up, 1, 2, and then 3p. So we have 1, 2, 3, 4. So it has 1, 2 unpaired electrons. Okay, try to do that for argon as well. I'm going to pause it and you pause it for about 10 seconds and then come back and see if you got it. All right, argon is very similar to sulfur. It's on the same level. The big key difference is that it has 6 electrons in that p orbital. So it'll have the same electron configuration, but all of the p orbitals will be filled. So it has no unpaired electrons. Just some defining of terms again. We call the electrons that are in the lower energy shells the core or inner electrons. They're the ones that are kind of tucked in. They're shielding the outer electrons or the valence electrons from the full extent of the nucleus. So for example, for silicon, we see that the electron configuration is 1s2, 2s2, 2p6, 3s2, 3p2. What you want to do is go to the last 2p or p6, right? That's where you end a row on the periodic table. And the higher energy levels, so 3s, 3p, this is the highest energy that these electrons are going to be placed in, and those are the valence electrons. So in this case, there are 4 valence electrons in silicon, and the other 10 are core electrons. So basically how an atom behaves, so the physical and chemical properties, is based on the number of valence electrons that it has. So these are the ones that are participating in chemical bonding. They're the ones that are lost when we make cations. And that's the shell that we're going to use to add the extra electrons to make anions. So here we have our nucleus, and then we have for silicon 1s, and there are 2 electrons. Then we have 2s, there are 2 electrons. Keeping in mind this is very simplistic because we really have 3 2p orbitals, but we have another 2 in there, and on the actual presentation this kind of comes in. That is where our core electrons are. Then in the 3s and 3p shells we have our remaining 4 electrons. So if we write the electron configuration for germanium, Ge, we're going to, and this one has 32 electrons because it has 32 protons. When we do the electron configuration, we've on the periodic table, we have the 1s and it's full, the 2s and it fills up, we have the 2p and then it fills up. Now we go down a row. Now we have 3s, which is full, 3p, which is full. We haven't got to germanium quite yet. We could go down another row. We have 4s2. We have to go all the way through the 3d, so 3d10, and then it's in the 4p2 position. So our core, well, first identify the valence electrons. Our highest energy level is 4, so we have 4 here and 4 energy level here. Those are our valence electrons. And then on the other side of things, anything below 4, so, oops, I'm actually going to do it in purple, 3d and 3 and 2 and 1, these are all of our core electrons. And I know it looks kind of weird how the 3d, it's kind of it's being sandwiched by the 4 energy level, but it is technically still part of the core electrons. So now I'm going to let you do this for phosphorus. And indicate how many valence electrons it has. All right, so now we can see phosphorus, it has 16 electrons in it. So we fill up the 1s, the 2s, the 2p. We go over on a new row, 3s, 3p is to where we get to. So we look, 3 is the highest energy level. There are 5 electrons in there, and then the ones before it are the 10 core. Now we are going to talk about the transition and intertransition metals. This is the D block and the F block. They don't follow the same kind of nice trends that our main group elements do. And so we'll see a little bit of weirdness, right? We already talked about the 3D showing up as a higher energy than the 4s, right? So we have 4s electron and then 3d, and then we go to 4p. So because there is this really actually small change in energy between the 4s and the 3d, it's like 4s, 3d, and then we get to 4p. That small amount of energy difference makes it actually easier for an electron from the s shell here to pop over into a d orbital. And so we actually get this kind of, well, I'll say irregular, but strange electron configurations for these types of elements, specifically ones that are really close to being half filled. So if we think about our d orbitals, if they have 1, 2, 3, 4, they're so close to being completely half filled or being completely almost filled. So if we have something that is has 9 electrons, so D9, look, it's only 1 away from being completely filled. Now when atoms are completely filled or half filled, their energies are lowered. It's more stable when electrons are not being repelled by another electron that's in its same shell, or when it is all the way matched up. So we'll see that with chromium, for example. Chromium you would expect to be argon's the last noble gas, and we have 4s2, 3d4. What we really have is 4s1, 3d5. So that electron, so if I have a 4s, let me erase for a sec. So let's say I have 4s and then 3d here. Chromium should be 4s2, 3d4. But then that electron on the 4s, the one that is paired, is actually going to be able to move over to fill that last d orbital. And this is actually more energetically favorable than the original one that we would predict. So copper ends up becoming, instead of 4s2, 3d9, it becomes 4s1, 3d10. We also see molybdenum, similar to chromium, it would also be 5s1, 4d5, so that a 1 is filled up. We weirdly also see something similar for rubidium. I'm actually not gonna, you don't have to worry about that. This one's a really weird one where it ends up being 5s1, 4d7. That one's a little bit, it doesn't fall on brand as much, so you're not gonna have to worry about that one. But even palladium, so the higher we go up in energy, the even more squish they get. So now something like 5s2, 4d8 would actually end up turning into 5s0, which means you don't even have to write it, 4d10. So both electrons in the s orbital are able to bump over, because that's just that much more stable when it's like that. So now we're going to start to talk about how electron configurations, and remember, these come from quantum mechanics, right, where you're talking about energy levels and orbitals. They help to explain a lot of the properties. We actually see elements that are in the same column, so same group, have similar properties. And that makes sense, right? They have the same number of valence electrons. So if we're looking at, let's say, beryllium's group 2a, they all have 2 valence electrons. Fluorine's group, they have 7 valence electrons. And the noble gases, which we'll talk about next, they have 8 valence electrons. And so it helps to explain the number of valence electrons an element has, and how it will then bond by either donating or sharing those valence electrons. So starting off with noble gases, they have 8 valence electrons. They are at the very last column on the right. All of them have 8 except for helium, which only has 2. And because they are 8, they are very non-reactive. And we basically know, for future reference, that all elements, especially in the main group elements, they really want to have electron configurations similar to noble gases. Their valence shell is full, everybody's satisfied. They don't have any need to want to react because their shells are full. And so, because they're very stable. So they have the full shell look, completely filled. The metals are making up the majority of the elements on the periodic table. If you remember, our periodic table kind of looks like that. We have our non-metals here, metalloids right there, and then the rest of it is metals. And so on the first 2 columns, we have group 1 and group 2, 1A and 2A. 1A is our alkali metals. They have 1 additional electron, so they have 1 valence electron, right? 1 more than their last noble gas or their core. And they are, because of that, they are super, super reactive. They would like to lose 1 electron to become like their noble gas, form a +1 cation. And so once they lose that 1 valence electron, their electron configuration is the same of their last noble gas. And so that stabilizes them. Alkaline earth metals have 2 more electrons than their last noble gas. They're in the second column, they're 2A. They like to lose 2 electrons, then they form a 2+ cation. And then once they do that, they have the same electron configuration of a noble gas, their closest noble gas. So that's why those electrons can come off a lot easier, especially in the metals, because they are really especially in the group 1 and 2, they're so close to their last noble gas if they go back a couple electrons. And so that's why they easily give up electrons. And when you're giving up electrons, sharing them, that's chemistry, that's chemical reactions. Now, transition metals and intertransition metals, this is the D block in our periodic table. Also the F block, I'll say that as well, F block. They are able to lose electrons from both their s orbitals and the d orbitals because they're so close in energy to form cations, but a lot of times these can have a variety of charges. So before 1a group, that's our alkali metals, they are always +1 every single time, 100%, no matter what. Group 2, alkali and earth, always +2 no matter what. Transition metals, they can do a variety of charges, but they'll always be a cation. Now, p-block metals, so I'm going to draw a periodic table again. If you remember that, it kind of looks like that. We have our p block here, right? And here's our s block, and then down here is our d block. So our metals are down below. They even go into the p block. So we have our p block nonmetals, but below the metalloids is our p block metals. And they can lose electrons from their s and p orbitals to form cations as well. They can also do a variety of things with their charges, similar to transition metals. Metalloids, we talked about on the zigzag. They are right here, right? They're located in the p block area. And they can act like either metals or nonmetals. They get used in things like superconductors, and they can conduct electricity similar to metals, but then they also have some non-metal type properties. And so when they do lose electrons to form cations, they do that from their p and s orbitals, or they could also gain electrons into their p orbitals to form anions. So here we have metallic behavior. So we have our nonmetals here, right, and our metals over here. So we'll see that the further away you get from the nonmetals, the more metallic you become. So like these guys have the most metallic capability, while over here it's a little bit less. Now our nonmetals are in the upper right-hand side of the periodic table. They are only in the p block. Now if we think about a p block, so let's say I have like 2s and 2p. So for something like fluorine, which has 2s2, 2p5, so our metals only had a couple in the 2s orbital, a couple of electrons there. So if they lose those, they're like their noble gas. Now once we get to the nonmetals, they're actually really close to they're like neighbors with their closest noble gas. So rather than losing electrons, they actually like to gain electrons, and they do that in their p orbitals, their valence shell, and that's how they become like noble gas. So they're always forming anions. So talking about the nonmetals, we have halogens. They are nonmetals. When in nature, so this is group 7a, in nature they actually exist as diatomic molecules. We talked about this before. They're always going to come up in a pair. They're not going to be on their own. So if I see fluorine, I'm not going to see just a single F atom. I'm actually going to see F2. There's always going to be a bond. Or chlorine, Cl2. It's never showing up as an atom. So in addition to these ones, and it really only goes to iodine, so bromine and iodine, we also have hydrogen forming H2, nitrogen forming N2, and oxygen forming O2. These are our 7 diatomics that you do need to remember. They all have one fewer electron. They all have that P5 configuration. We can see 2p5, 3p5, 4p5, and so on. And so they're really close. If they gain an electron, a single electron, they become like the closest noble gas. So they all form a -1 charge. And so when they react with other nonmetals, though, so these are actually kind of special because if they react with a metal, they form an anion. They form a negative charged ion. If they react with another nonmetal, though, they tend to share electrons, and and that's the way they get to be like the closest noble gas, is by sharing rather than a full transfer of electrons. So they have a variety, and this is how we actually form molecules. We can think about something like water. It is a molecule, and so it shows up like this, where oxygen is actually sharing electrons with the hydrogen. So when I form an ion, I can use the periodic table to help me figure out the charge, specifically for our main group elements. So for our alkaline earth, our alkaline metals, group 1A, they're always going to form that +1 charge. Our alkaline earth metals in this 2A column, they're always going to form a 2+ charge. Note that this is incorrect. I don't know why there's a +1 there. They're all +2. Our halogens, being very close to being a noble gas by gaining an electron, are all -1. And then the group 6A, the chalcogens, are all -2, because if they gain 2 electrons, they become like their noble gas. And nitrogen even gains 3. Other ones I actually want you to know are that aluminum is always +3, zinc here is always +2, and silver is always +1. So we have a 3, 2, 1 kind of stairs starting with aluminum. So again, alkaline metals always form +1, alkaline earth always form +2 cations. Transition metals can have a variety except for these 3 that I listed. And nonmetals are the negative ions when they transfer electrons. And our halogens here always form 1- anions, and the other nonmetals can form a variety, but I will say chalcogens are also always consistent, and nitrogen is always consistent. So if we predict the charges, looking at where they show up on the periodic table, aluminum, it's a metal. It's on the left-hand side of the metalloid zigzag. It has a 3s2, 3p1 configuration. So it's actually going to lose those to become Al3+. Now sulfur is really close. It's in the nonmetal region, so we know it's going to gain electrons. If it hops over 2 to the right, it'll become like its closest noble gas, which is argon, and so sulfur will become S2-. Now nitrogen is also in the P block to the right above the metalloid, so it's going to form an anion, and if it jumps over 3 to the right, it'll become N3-, and that is its charge. Then rubidium is in the first row. It's a 3s1. Nope, not 3s, sorry, 5s1. And so it's going to lose that electron and become rubidium will turn into Rb +1.